So this is the 13th lecture in the series, and we are going to explore more on groups. To begin with, let's recall the fundamental theorem of arithmetic, more intuitively known as the unique factorization theorem, which essentially states that any positive integer greater than or equal to 1 can be written as a product of prime numbers in exactly one way. Of course, not referring to the order of the occurrence of those numbers, which implies that, okay, suppose we have the number, mm, say 63, which will uh, which can then be expressed as 3 into 3 into 7, where 3, 3 and 7 all are primes, and or this can also be written as 7 into 3 into 3, or in any other sort of arrangement that wouldn't affect the statement of the theorem. Okay, moving ahead. Let's come to, sorry. Hmm. Now, this theorem states that the fundamental theorem of finite abelian groups states that every finite abelian group is isomorphic to a direct product of cyclic groups of prime power order, which means let's consider an example. Let's consider an abelian group of order 60. Basically, an abelian group means a group such that every element of the group will commute with every other element of the group. Let's consider a group of order 60. Since the order of the group is finite, we can clearly see that it is a finite abelian group. And when factorizing 60 using the unique factorization theorem, we end up with the factors as 2 into 2 into 3 into 5. And we get 2 square into 3 into 5. With this in mind, moving ahead, uh, the fundamental theorem for finite abelian groups states that if we wish to classify all abelian groups of order 60, we have the following possibilities. Recall we had 2 into 2 into 3 into 5. So this can be stated as Z2 cross Z2 cross Z3 cross Z5. With this, the cross represents the direct product. Or we could also have written it as 2 square into 3 into 5, and hence it can be written as Z4 cross Z3 cross Z5. Similarly, we can classify other finite abelian groups. This is the more rigorous more formal way to state it, which is every finite abelian group G is isomorphic to a direct product of cyclic groups of the form ZP1 alpha 1 cross ZP2 alpha 2 cross such that ZPn alpha n, where PI's are primes not necessarily distinct. When we go back to this example, we see that here 2 is a prime, 2 is again a prime, 3 is a prime, and 5 is a prime. Here, 4 is not a prime, but 2 to the power 2, where 2 is a prime, and 2 becomes alpha, which is raised to the power here. Moving ahead, let's come to P groups. Uh, I'll be borrowing my definition from Dummett and Foote, the classic textbook on abstract algebra here, which states that a group of order p to the power alpha for some alpha greater than or equal to 1 is called a p group. Now, of course, alpha will belong to the set of integers and must be greater than or equal to 1. Here, p represents a prime number. Okay. So, here, any group of the order, say, 2, 2, 2 square, 2 cube, or take any other prime number, say 7. So 7 square, 7 to the power 5 for that matter of fact, will also form a p group. That was the basic definition. Now, coming back, subgroups of G, which are p groups, are also called p subgroups, as normally the definition goes for a group and a subgroup. Same applies for this case. Let's get to Silo P groups. Now, consider a group G of order p to the power alpha m, where p does not divide m. So let's say we consider a group of the order to the power 3 into 3. Now clearly 2 does not divide 3. Then a subgroup of order p alpha is called a Silo p subgroup of G. So to the power 3, 8 is essentially 24. Now for a group of for a group of order 24, we have Silo 2 subgroup or a 2 Silo subgroup of G whose order will be 2 to the power 3. Now why 3 and not 2 or 1? Because for a Silo P subgroup, the order of the Silo group must be the highest bar of the prime mentioned here. That is the alpha. I think we'll better understand this with other examples. Let's move ahead. An example perhaps. Let's consider a group of order 45. So for a group of order 45, that is we have 3 to the power 2 into 5. That means that there exists one 3 silo group, 3 silo group, and one 5 silo group. But the order of the 3 silo group would be 3 squared and not 3. Okay. Taking another example, uh, let's consider a group of order 450, which is essentially we have just multiplied factor of 5 into 2 to 45. We get the order 450. Now for this specific group of order 450, uh, we have the factors as 3 square, 5 square, and 2. So there exists one and only one 2 silo subgroup of order 2 and another 5 silo subgroup of order 5 square and another 3 silo subgroup of order 3 square.
Okay. Okay, so Lie groups, class groups, and categories here. I'm just gonna give motivations around these topics, not gonna go in much depth unless needed. Okay. Okay, so Lie groups, okay. So first, uh, the person who is credited with most of the discoveries in groups is Galoha. And Galoha used to think of groups as something which tells us the symmetries uh, of some space or some object. So we write the symmetry of an object as a group. So what does it mean to have a symmetry of a group? So for instance, you you think of a hexagon or you think of a circle. On a circle, even if you do an infinitesimal rotation, the circle is invariant. Yes. So for that, I can just do this. Yes. Okay. Where is? Yeah, this is a circle. Or let's take something like a triangle. So here, a infinitesimal rotation it keeps the circle invariant. That means circle remains constant. It doesn't change. But here you don't have that liberty. You have a specific degree of rotation that is needed to keep the triangle invariant. And I think we saw this in dihedral groups when we were discussing this. Yeah, so every object has some sort of specific symmetries, And we will call that symmetry group as symmetry of S. So S is an object, and the symmetry of the group will be called. Uh, and actually, the symmetry of a group, sorry, symmetry of an object is a subgroup of isometries. And isometries is something that you study in topology. Isometries of a space. Basically, isometries are the symmetries of a space, uh, which are not needed here to discuss in group theory, but still, in topology and perhaps in differential geometry, you are required to study the isometries of a space. So for that, the isometry of a Minkowski space, of a de Sitter or any space, so that, like, the isometry of this space that you are living is basically the Lorentz group SO1 comma 2, if I'm right. Anyway, so now we are talking about Lie groups, and Lie groups are something which takes up algebra and geometry. So you have algebra that is coming from groups, and that algebra is what? That algebra is basically the binary operation that you study very exhaustively. So now we will take a smooth differentiable manifold, M, mostly real, but even if you change the real manifolds to complex, it doesn't change much. It's still the same. So what is meant by smooth and what is meant by differentiable? So you know what is differentiable. So on a manifold, M will be called differentiable if you can, if you can differentiate it. Uh, so I think you have understood, you understand what is continuous and what is differentiable functions. Yes. So manifold is just that, where every point is differentiable. And smooth means, say, infinity. That means every function can be differentiated up to infinite power. Like, for example, x square is differentiable to 2. Yes. Like x squared 2x and then 2 and then 0. Yes. That. So a function is called smooth when it is a C infinity. So C square C Q is basically how many times you can differentiate. Yes. So
So does it mean that it can be differentiated an infinite number of times?
yes.
Okay,
Okay.
okay. Thank
Yeah. So smooth function is that. Sorry, I should have written here M. So when you consider a manifold is basically what? A manifold is a topological space that is locally homeomorphic to Euclidean space. That is a meaning that just say a manifold is locally nothing but Euclidean space. Yes. So a manifold has but a topology. Yes, it has a metric on it. So that metric we can call, let me call that metric somewhere. Let's call it, I don't know, mu. Let's call it mu. A mu is a metric. Yes. What that tells us the distance between 2 points. Yes. A metric in topology is that it
you. Yes,
tells you
yes.
the distance between 2 points. So a manifold has a metric. Okay. And now when M is also a group, that means what? A group meaning these axioms that you have. Now, when a group, sorry, when a manifold is also a group, yes, then it is called a Lie group. What it means is that, see, you have some sort of operations in a group. Yes, G cross G goes to G. Yes, I mean, this is a binary operation. That is a closure. Yes. So these operation, let's call it multiplication. And division in group is nothing but taking inverses. Yes. You understand this? I mean, inverses means just the division property in group. That is not available in rings, but in group it is. So we'll call the inverse as something like this. So, for example, every element in a group has an inverse, and every element under this composition will also be in the group only. So these things, these and the inverses. How do I call the inverse thing? Let's see. Um I can create a map. Let's say from G inverse goes to G. Do not get confused. This is just taking the inverse of an element, and this is taking, all right, there will be some noise coming out. Anyway, so uh, let me just mute myself for a minute. All right, I think we can continue. So, what I'm saying is that these are the operations you have: multiplication and division. Similarly, in the same analogy, you can have addition and subtraction. So, what I'm saying is that these operations are also smooth. So, M is a manifold, M is a group 2. This is a group, this should have been M. M is a group 2, and these operations that you have been defining are also smooth. And then it is called a Lie group. This was Lie, Sophus Lie, if I'm right. So basically, this becomes a group of continuous symmetries. You know, continuous, that means what we just discussed in the circle case, that even an infinitesimal rotation keeps it invariant. While in triangle, it is discrete symmetry. You know, you don't have a continuous symmetry. So, so we need a manifold that has smoothness on it. That just means that it doesn't have this discreteness. I mean, it means that. And you see that M is a group too, then it is called a Lie group. So basically, you have algebra and geometry side by side. And why this is important, Lie groups? This was very important, at least from the point of view that it takes two subjects together. And the thing is, all of these representations of these Lie groups, basically the what we discussed last time, representation of a group is basically its map on the automorphism of a vector space. Yes, the automorphism group of the vector space. So basically, you take the groups, elements of the group, and map it to some sort of vector space. And ideally, it is a matrix. Yes. So that. So a Lie group's representations are very important in physics, and the examples include SU2, SU3, SO3, and U1 is also U1 is basically the group of circle symmetries. So U1 of circles is basically S1. S1 is basically a group. It's a circle group. Contains the elements Z. The modulus of Z is 1. Okay. Sorry. Clear. Okay. So similarly, this was a Lie group, but not every okay, so manifold has a topology, but not every topological space is a manifold. This is a fact. So when you don't have a smoothness in it, but you still have a topology defined on it, a metric defined on it, you can call it a topological group, where it is nothing but the groups and topological spaces. So for us, it is the Lie group that we want to discuss, not the topological group. So yeah, as we said, group has a group structure with a binary operation. It also has a manifold structure, and smooth binary operation yields. A smooth binary operation means a binary operations were described in the group that has to be smooth in this. Yes. So these are the Lie groups, and the examples are SO2. SO2 is basically a group of rotations in 2 dimensions. Yes, like you have cos theta, sine theta. Sorry, I believe this cos theta, sine theta minus something and cos theta, if I'm right. I don't know. But the group of rotations in 2 dimensions, those are uh, Lie groups. What that means is it's also a manifold. SO2 elements are also on a manifold. That is what we are saying. SUN is also important. So UN is unitary group, and SU means special unitary groups. U1 is the one we discussed, the circle symmetries. The U1 is basically the group of circles symmetries. Lorentz group and Poincaré group are very important in GR perspectives. E8 and E6. Now, what does E8 and E6 are? E's are called exceptional Lie groups. These are called exceptional Lie groups. These are groups of very high order, actually. And yeah, I won't be discussing this, but the fact that E8 cross E8 is uh, one of the valid groups in string theory is also a fact. Anyways, what I'm saying is that these Lie groups are very important from physics perspective as well. so that the representations of these Lie groups are very, very important. Yes, because they are telling you what are the particles in a specific theory. For example, the U1 is basically a Lie group, and its representations are very important in electromagnetic theory. Similarly, you have SU2, which tells you the representations in weak theory, and SU3 basically tells you the representations, strong theory. Anyway, so one can also have a p-adic Lie group. Basically, what that means is, this is a little out of our subject. What is a p-adic field? Yes, and those are the metric completions of the rational field. Anyway, what I'm just saying is that we can have much more than what is asked for in these areas. Yeah, I'm not going to discuss what is metric completion of Q. This is a little bit different. Anyway, so I think a Lie group is that. This is just the motivation behind it. What I'm saying is that group is not just group. It can also be combined with many other things, and you can take much mathematics out of it. Yeah. Yeah. So now something which is very hard to talk about in a series on group theory. What are the principal ideal domain in the class group? So I didn't want to discuss rings and fields in this, but we need to discuss this because it's very important to describe what is a class group. Now, class group is a group. That's why we included this in the series. And also to motivate why when you think that the unique factorization, something that Purnima just talked about, yes, that is a fundamental theorem of arithmetic, tells you that any number can be written as a product of power of prime numbers. Yes, so that doesn't hold in every situation actually, and this is what we are going to discuss. So a ring is some sort of algebraic object. It's an algebraic object where the elements of the ring also follows some axioms like groups, except that not every element has to have an inverse. All right. So we're not going to go in depth in the definition of a ring. But yeah, so a ring has an ideal. Like, ideal is basically this, that so if you have an ideal in a ring, then basically IR will belong into I. Sorry, what is that? All right. So let's take a Z as a ring of integers, and let's take a 2Z as an ideal in that. So basically any element taken from these two, and if you take a multiplication in them, they will just be here only. Yes, like this is very simple fact that any number multiplied with an even number is an even number again. So 2Z is an ideal in the ring Z. Now, an ideal is called principal when it is generated. Okay. Yeah. When it is generated as a power uh, of an element. Okay. Yeah. All right. So basically, any Z is basically that. You show this, yeah, in a cyclic group case. Yes. So in a ring R where every ideal is principal, then it is called principal ideal domain. And this is a very important theorem to show that every PID is a UFD. That is to say, every ring which admits which is a principal ideal domain has a unique factorization case. That is what we discuss. Yes, like 16 is written as just one way. There is just one way to show that 16 factorizes in prime numbers. Yes, but this will not hold if your ring is not a principal ideal domain. Yeah, and the proof is so what you generally do is you prove this for Z, and then that proof holds on for any PID. You have to show first that Z is a PID. What I just took it for an example. You have to show this. For that, you need to know what is an ideal in principle in much more detail. Anyway, so our focus was this basically. Yeah. Yeah. So when a ring is not a principal ideal domain, the factorization is not guaranteed actually. So this is very important theorem. Now, when the unique factorization is not guaranteed, that means that an element can be factored in not just one way, it can be factored in two ways. Yes, that is the failure of unique factorization. So what class group does is that it measures how the ring of integers in a field K, and okay, wow, these are heavy words, but every field has a ring of integers associated with it. This is, let just take this as a fact. You may inquire this later. So every field has a ring of integers. Integers, this is a Z, and ring of integers is always associated with a field. Anyway, so class group tells you how the ring of integers in a field K fails to be a unique factorization domain. And class group is nothing but this quotient group, where the JK are the group of fractional ideals and PK is a subgroup of principal ideals. It will take us a while to get to these definitions very properly. I'm just trying to motivate something here. That class group tells you how the factorization fails in a field. Now, field is also an algebraic object where the inverses are taken, not like a ring. So, for two things to take away: not every ring will admit a unique factorization. Although this is very easy to prove for Z, yes, and this is what we call fundamental theorem of arithmetic. That is actually nothing but showing that Z is a PID and that has a unique factorization domain. So, in other words, it says that. Anyway, and the order of this group is called the class number. And if the class number is 1, then it is an UFT. And you can show that the quadratic extensions in the positive number. What is a quadratic extension? I think so. Basically, you write like this, yes, where D is a square free integer. So these have class number ones, and you can show similarly. Anyway, but some of these quadratic extensions will not admit UFTs as well. And yeah, so class group is nothing that group theory course should inherit. It's a subject in class field theory, which is an algebraic number theory problem. Anyway, the motivation was just to show this, that okay. Anyway, the last thing that we wish to conclude on is this: that group is a structure, and what we saw all together is that mathematics is built of these structures: a group, a ring, a manifold, a topology, uh, a field, or something like that. So the ultimate goal of mathematics is to study these all together, and that is where the category theory comes in. So it was mostly done by two people. I'm forgetting the one name. It's Saunders MacLean and Allenberg. Yes, Samuel Allenberg. These two people are credited with much of the category theory history, also a bit of Grothendieck and all. So, what is a category in mathematics? So, a category is basically a collection of objects and morphisms between them. No, okay. So, what you do is even groups is that, yes? Even a group is not a category. What I'm saying is, even in group, there are elements and they are related to each other by some sort of binary operations. Now you take this to a very high level. You say a category will have algebraic objects and morphisms between them. So what you can do is you can create a set of stuffs, yes, like an apple, banana, orange, and so forth. So what this becomes is it becomes a category of fruits, and they are related to each other by some sort of morphisms. So everything in mathematics forms a category, like a category of sets, in which the objects are sets itself. And yeah, so in category of sets, what happens is you have You have the objects as sets, and the morphisms become the sets morphisms. Yes. So a category of the group basically means that the groups that we have been studying so far, category of abelian groups, a category of non-abelian groups. That means the groups will become objects, and the morphism between them becomes the group homomorphism that we have studied in detail. So what you can imagine now, I'm failing to give you a visual idea, but trust me, it's beautiful. So what category theory is, it's that tells you that these algebraic objects form a cluster. Okay, you can imagine constellations. Yes, you can imagine constellations. Now every star in this constellation is related to another star by some sort of morphism. And what I'm saying is that it doesn't yeah, that. So a category of the group basically is that. And as I said, every mathematics has some sort of category, like category of sets, that category of topological space, category of metric space, category of groups, category of rings, everything, in which the objects become some sort of algebraic object and the morphisms between them becomes some sort of special morphism. So here in the case of group of category of the group, it becomes group homomorphisms. Now you can write a sequence. For example, let's say I have a category of groups, yes, G1, G2, G3, and so on. So what I'm saying is that this is a category of a group. So all of the objects in this will be groups only. And the morphisms between them becomes a group morphisms. So there'll always be a morphism like this, G1, G2, G3, and so on. So this is called a sequence, a chain. Now, you might know what is the kernel of this function or the image of this function and so on and so forth. Yes? And these homomorphisms will become isomorphisms when there is a bijective mapping. There will be monomorphism, epimorphism, and so on and so forth. So I think we have done this many times. So there is always an initial object. So initial object of this will be that it will be an object from which we can map to any other element of this category. And the final object will be, so for example, initial object is nothing but I goes to G, and final object will be G goes to F. So there will be existing only exactly one morphism. So initial object I will be something like this, from which we can take a morphism to any other element in this group. A final object is basically something to which we take exactly one morphism. And if an object is both of these, then these are called zero object of the category. And the zero objects of this group are groups with only identity. Those are the trivial groups. So now these are some things, you should read upon these. Now, what is a functor? A functor is between two categories. As we said that, anything can form category. A category of sets, category of groups, category of topological spaces, and so on. So now what you can do is you can define two categories, C1 and C2, and you can say that there exists a map between them, yes? And that is called a functor. What will it do? It will take the objects in this and map to the objects in this, and will also take the morphisms in this and map to the morphisms in this. All right. So there exist categories like group that we studied, but there also exists category of monoids, category of topological space, and category of sets. So there always exists a forgetful functor between groups to monoid or groups to sets. All right, I'm running short on time, so I'll just end it right now.